Hello people, Zach here again today, and this is actually going to be a math video, believe it or not. This is going to be an intro to calculus for people who have a difficult time trying to wrap their minds around the way that the calculus operators work and how to set up problems and stuff. And the main reason I wanted to do this is that I'm personally a self-taught when it comes to calculus, and so I have my own set of intuitions and things that I wish that I had learned early on that I feel like no one ever took the time to explain. And even when I went to college and they were trying to explain this stuff, I don't feel like they did a very adequate job of trying to show people how you would set up problems and why you set them up the way that you do. So let's go ahead and get started. So say we have some value. We're going to call it x sub a. And if we added some change to it, like a change in x, which we're going to call delta x, we'd imagine that we would get a new value, which we're going to call x sub b. And of course, what this means is that x sub b is equal to x sub a plus some change in x. And by the rules of algebra, we could have also rewritten this as x sub b minus x sub a is equal to delta x. Fairly straightforward thing so far. Now, here's something interesting, thinking about this delta x for a second. It would still be delta x if we cut it into cut it into thirds, and then added all three of them together. So if you took a third of delta x plus a third of delta x plus a third of delta x, and added them all together, you would get delta x. I don't think anyone would argue with that. Of course, this would also be true if we added together 5 1/5 of delta x. Or if we added together 7 1/7 of delta x. Really doesn't matter how many pieces we cut it into, as long as we add them all back together to get back to the whole. And so a way that we can kind of generalize this concept is that we can say that if we add together I is equal to 1 to n of 1/nth of delta x, that we would get back to delta x. This would be true no matter what value of n we do. And bear in mind, this I doesn't have any significance at all. This is just kind of our iterator telling us where we start. So if we put 3 here, I would go I is equal to 1, I is equal to 2, I is equal to 3, adding up all the terms, and it'd just be 1/3 x plus 1/3 x plus 1/3 x. So it's the same thing as this right here. And because this would be true no matter what value of n we put in here, it would be true even if n was infinite. Now, of course, we can't ever actually get to infinity, but we can always pick of any value, like arbitrary value that's bigger. For any value you give me, I can think of an even bigger value for which the relationship would hold. So we're just going to kind of express that kind of idea in a more rigorous way by saying the limit as n goes to infinity. And rather than trying to write this whole mess right here, which is just a pain in the butt, that's a lot and kind of weird to look at, we could just put this, the integral from a to b dx. And what this actually means, this is just a notational trick that means the same thing as this right here. But this a and b, where it's coming from is the b and a that are here for this delta x. So that's where that sits. So it's for this interval from a to b, the sum of all the small parts of x, the small fragments here, is equal to the whole. Now, before we can move on from here, I think I'm just going to go ahead and write this in a way that's going to be more useful for us. So this right here is our golden relationship. This is what we care about, and if we stare at this long enough, we can figure out all of the secrets of calculus and like how it all applies. So let's just go ahead and build up from here, and you'll see what I'm talking about. Let's suppose we're dealing with a rectangle, and we want to know its area. Well, the area of a rectangle is width times height. Well, what is width? Width is just a change in x, right? And height is just a change in y. Well, if that's the case, then based off of how we've defined this delta x here, we should be able to say that that's equal to the integral from a to b, of dx, times the integral from a to b of dy. Now, this is true, though it's a little bit ugly to look at, but if you think about it, you know, we should just be able to move that integral over there because we're just saying that we're adding things, right? So integral from a to b, that was the integral from a to b, dx, dy. That's a little bit better to look at, a little more organized. And congratulations, you just discovered double integrals, which you normally wouldn't get to until multivariable calculus. Well, what else can we do? Let's try something else here. See, linear equations, the slope of a line is equal to the rise over the run, which is the change in y over the change in x. And of course, what this means is that we can get the rise, which is the change in y, by multiplying the slope by the run, which is the change in x. So this delta x cancels out the delta x in the denominator, and you get delta y back out. And of course, if this is true, then this means that we should be able to do m is equal to the integral from a to b of dx, and this would also be true. And in fact, it is for a line, at least a straight line, where the slope is the same. So what if we had a nonlinear line? Well, of course, linear line, you have a straight line here, which means the slope is the same no matter where you're at. And a nonlinear line means that the slope changes. So as we're here, we see that the slope is positive because the function is increasing. And then once we get to here, the slope starts going negative because the function decreases. And then the slope becomes positive again, so the function starts increasing. Then the slope becomes negative again, it starts decreasing. And so if we labeled our axes here, y and x, what we can see here is that as we're going along to the right on these x-axis, that our slope is changing, so our slope is sort of dependent on our x. And of course, when we say that the slope is dependent on x, what that really means is that slope is a function of x. So if we know that slope is a function of x, let's try and rewrite this to make it work for a nonlinear function and see what we can get. So we start off here with, say, delta y is equal to m of x times the integral from a to b dx. Well, hold up here. This slope is a specific slope, which is dependent on a specific value of x. But which x are you talking about? Are you talking about a, or are you talking about b? I mean, it can't be a delta x because x is not the same thing as a delta x. So that doesn't even really make much sense. So we can't write that. That can't be right. It's ambiguous. It doesn't make any sense. Let's try it this way. Let's do a to b of m of x dx. Okay, so now this makes a whole lot more sense because remember, we're just iterating here through from 1 to n. So we can imagine it's the first x, and then the second x, and then the third x, and then the fourth x. So this mx is referring to this, basically like this I value for m. So that makes more sense, right? But think about the definition of m here. This definition of m is this delta y over delta x. So if we try to expand that here, see this delta y over delta x. Oh my gosh, can't write today. Delta x dx. Uh-oh, what happened here? Okay, so look here. This integral of a to b of dx, that's equal to delta x, but dx by itself is not the same thing as delta x. So we can't really simplify this expression in any way, and if we can't simplify it, then obviously it can't be the same thing. So that means that we actually can't do that. Although it did look like it made sense, we can't actually do that. But if we think about it for a second, this is just a change in y over change in x. Well, what if we had a really small value of x? Now, obviously, we can't go to 0 because if we went by 0, if we divide it by 0, it would be undefined. But consider the fact that for any change in x, it's implied that there is or isn't a change in y. But the inverse isn't necessarily the case. If there was no run, but there was a rise, what you would have is a vertical line like that, because you're not going any further to the right, but your rise is going up, and that's not a function. So really, it's this delta x implying this delta y. And so if we had a really small run, like a dx, that would imply a really small rise, dy. And so maybe we could think of this function over here, we could say, what's the integral from a to b of dy over dx times dx? Oh, look at that. Now this dx right here will cancel out the dx in that denominator, which would just leave us with the integral from a to b dy, which is, in fact, delta y. So just to go ahead and summarize what we just did there, what we arrived at was this conclusion for this right here. And what happens if we expand that delta y? Because remember, this delta y is a yb minus a ya. So we can say that's yb minus ya. It's going to be equal to the integral from a to b of dy dx dx. Well, what if we put that a on the right-hand side there? What that would do is it would give us a to b of dy dx dx plus y sub a. Now, what's interesting about this is that if y is a function of x, and you give me any ya, I can tell you what the yb is going to be if I know how y changes with respect to x. And what does that actually mean? Like, how is that useful? Well, to consider how this is useful, let's look at a completely different problem. Let's suppose that we have an object whose color changes over time, which means that its color is actually a function of time. If the color that it is at 3 seconds is different than the color it is at 5 seconds, or so on and so forth. And so what this sort of implies is that for any period of time, delta t, there's going to be some change of color, which could be 0, could not be, but the general idea is that for any change in time is what implies a change in color. And of course, the way that color changes with respect to time would be change in color over change in time. And what that implies is if we can do this, then we could do the same thing for an indefinitely small period of time, where we would arrive at an indefinitely small change in color. And based off of this expression right here, what we would see is that the color at time 2 is equal to the integral from time 1 to time 2 of the change in color with respect to time, plus the color at time 1. So if you tell me what the color is at time 1, I can tell you what the color is going to be at time 2 if I know how the color changes with respect to time. And what's really interesting about this is not only is it a method of solving all different kinds of problems that are related to things changing with respect to time, but this whole thing we've been doing here, we can basically do this on pretty much anything that we can add and that we can subdivide these differences from. Like, take for example, let's say we were doing vectors, right? Well, we can consider the fact of a vector A, the difference between a vector A and a vector B, right? Like, we can subtract vectors, we can do that, right? Well, if we can subtract vectors, well, then that means that we can kind of more or less define the notion of like a change in a vector. And if we can do that, and let's consider like scalar multiplication. Well, we can see add together 3/3 of a vector, right? We can do that. This would be true like if we did 1/7 of a vector and then added it together 7 times. So we can do that. So what this means is that we should be able to do this as well. No, I've never seen, someone do this in particular, but as far as we can tell, based off all the rules that we've seen before, this should be correct. But here's another thing as well. Like, if you're familiar with vectors at all, there's something called the dot product. And so you can imagine the dot product of vector u times the dot product times vector v. I just tongue-tied myself. Vector u dotted with vector v. Now, this is actually yields a scalar value. A scalar value is just a normal value like this, like x sub a, or something like that. That's all a scalar is. Now, in physics, what we know is that the amount of work that's done is equal to the amount of force times the distance that you apply it. And of course, what this intuitively means is that if you haven't moved an object, then you haven't done any work, and if you haven't applied any force, then you haven't done any work. So if the object moves itself, you're not doing any work. And if it doesn't move at all, you haven't done any work. So what if we were dealing with a case where this wasn't a linear distance? Like what if, or something like that? Well, if we can write this in a different way, we can think of it like this. We can say that the force, with respect to some space, like with force with respect to position, like where you are, like the force is being applied, dotted with some change in distance here. As you go from A to B. Now this seems like it's kind of weird, right? This is kind of... I'm trying to think of a good way to explain this. So what we're doing is we're sort of like projecting this force vector onto the space. So what we're seeing is, like, imagine if you had a line that's like this, like you had a vector here and a vector here, right? This vector that's right here, this u vector, and this being our v vector, there's a part of it that is parallel, that goes like this, and that would be u parallel to v, and then there's a part of it that's perpendicular to it right here, which would be the u, that's the part of u that's perpendicular to v. And when you take the dot product of two vectors, what you're doing is you're taking this part right here, this u that's parallel to v, and multiplying it by v itself. But you're not getting a vector out of that. What you're getting is the product. So if this is 3, if this length was 3, and this length right here was 6, u dot v would be equal to 18, because 3 times 6 is 18. So the same thing would happen is, like, if we imagine if we had a vector where our force vector was here and our space vector was here, that doing this dot product kind of projects the force on here, and it's telling us how much the force is acting in the direction that the object is moving. But anyways, what that does is that simplifies down to a small amount of work being done, which is a scalar, not a vector, because the result of a dot product is a scalar. And of course, that's going to be equal to the total amount of work that's done. And so, yeah, we can do calculus on vectors. It all works out. And like I said, you can do calculus on pretty much anything as long as you can, like, add and subtract it, and you can subdivide it. If you can do that, then you can do calculus on it. But I feel like all of this becomes way more intuitive once you understand this, because if you understand this, you can derive the rules of everything else from that. And I really wish that I could have found anyone at all who would have just written this on a blackboard. If someone would have written this on a blackboard somewhere, some point in time, it would have saved me months of learning time just trying to figure out how everything else worked. But that's pretty much it. I hope this was helpful. I might do another follow-up video where I go more into the arithmetic, or maybe kind of maybe more into differentiation or something later on, maybe not. But I hope this was helpful, and thank you for watching.